showing 87.81% CIFAR10 accuracy with 2.6 megabit on-chip parameters in a 28 nanometer FPGA. This is the outline of my presentation. It consists of introduction, proposed processor, results, and the conclusion. Binary neural network reading single-bit elements from input features and weights still require external off-chip storages. For example, it is as large as for 13.7 megabit for bridge-like model targeting CIFAR10 classification. It is considerably large to efficient inference processor. So many previous researchers developed the parameter reduction techniques such as group convolution and global average pooling, but they are not supported efficiently in previous work. Therefore, we proposed the BNN inference processor to execute these parameter reduction techniques. In our BNN inference processor is based on the unified processing mechanism supporting the parameter reduction techniques with high resource efficiency and realizing inference with on-chip parameters affordable to fit in a low-cost FPGA. From now on, I will present about our proposed processor. In the proposed processor, multiple output elements are computed in parallel over multiple steps, and external results are accumulated in parallel in association with the output channels as illustrated in these figures. In these figures, we can see a common computing mechanism sharing across the convolution, group convolution, and global average pooling. Because various BNN blocks can be processed based on this unified mechanism, there is no resource overhead. Based on the unified mechanism presented in the previous slide, we developed an efficient microarchitecture for the BNN inference. This is the microarchitecture of proposed processor. The architecture is designed based on a 128-way synced processing pipeline. And to support various block operations, input multiplexing is employed for the external operations. And notably, we can see no adder tree in this part. So the proposed processor can achieve scalability in inference speed. The reason why no needing an adder tree is because the partial sums are computed incrementally by the 1-bit external operations. A fully integrated prototype inference system is developed in an FPGA. This is the overall inference system with the proposed processor executing per block operation of the developed model consisting convolution, group convolution, and global average pooling. Because all the parameters are stored in memory, there is no off-chip data transfer and MCU intervention during the block operations. After completion of the all operations, the classification result can be shown as follows. This is the implementation result. Owing to an adder tree-free and unified mechanism, the proposed processor exceeds 79.97% lower logic resource usage than previous work. As a result, the proposed processor supports a model that can achieve comparable accuracy with only 2.6 megabit model parameters. In addition, its VRAM resource usage is just 2.9 megabits. Despite the fact that every parameter is stored on-chip memory. This is the functional demonstration video. The prototype inference system is integrated into FPGA. The images surrounded by a green box indicates correct results, and the images surrounded by a red box indicates incorrect results. Here is the conclusion of this work. In this study, we designed and implemented an efficient processor for BNN inference with on-chip parameters only. The proposed processor is developed with novel unified processing mechanism to support various parameter reduction techniques such as group convolution and global average pooling. And the microarchitecture is based on a resource-efficient adder-tree-free output parallel architecture, and its functionality is fully verified in an FPGA-based inference system as demonstrated in previous slide. As a result, we have developed a resource-efficient BNN inference processor whose parameters are stored in on-chip memory. This is the end of my presentation. Thank you.